Well, good morning, everyone. Nice to see you. Nice to see a good turnout here. And I'm just here to briefly introduce Kyle Thompson, our student, who's not only an expert at how single photons interact with atoms and the stuff that he's going to be telling you about today, but also our local expert in filling balloons with nitrogen, which we can all tell you about some other time. Anyway, without further ado, over to Kyle.
Thanks. All right, can everyone hear me, first of all? Good, yeah, okay. So yeah, thanks everyone for coming. Today I'm going to talk to you about the question and the title of this talk, which I've been working on for the majority of my PhD. Okay, so basically to kind of set the stage here, we're going to be thinking about a system which is a cloud of two-level atoms and a photon that is somewhere near resonance with those atoms. And basically in a scenario, kind of one of two things can happen. Either the photon will be transmitted through the atoms in the same kind of direction, or it will be scattered off to the side somewhere. Okay, and so the question that we're interested in here is essentially, as this photon was propagating through this cloud, how long did the energy of that photon, let's say, spend in the form of an atomic excitation? Okay, and in particular, the interesting part is, does that answer depend on what happens to the photon? So for example, if it's transmitted, it didn't scatter it off in any other direction, maybe that means that it didn't talk to atoms at all. Okay, so that's kind of the basic thing that we're going to be talking about today. So here's like roughly the outline of the talk. So because this is a longer talk than I usually give on this topic, I wanted to start with a bit of sort of historical background of how we got interested in this question in the first place. And then we will switch to talking about what happens to transmitted photons. So this includes a first experiment that we did before we had any theory for this question, together with a theoretical prediction, and then a second experiment trying to confirm that theoretical prediction. And then lastly, I'll talk a little bit about scattered photons and what's predicted for those, and in particular, my plans to measure this other kind of scattered excitation time. Okay, so part one. So basically, the experiment that I work on usually does this kind of stuff. So we basically do single photon level nonlinear optics with a gas of cold atoms. Okay, so the basic idea is we're trying to kind of generate effective interactions between photons, and you can imagine using these for trying to build something like a C0 gate for photons, for instance. So we've done some work on, for example, the nonlinear phase shift due to a single photon. We've done a weak value amplification experiment, very similar to that, where we kind of amplify the effect of one photon. And then we've done some other work with Rydberg atoms, for example, also trying to generate these kind of strong interactions between light. Okay, and so all of these experiments kind of have a similar structure. So I don't want you to pay too much attention to the technical details of this, but essentially the structure of these experiments is that you have some pulse, which we're going to call the signal, which travels through a cloud of atoms and does something to them. So in this case, the signal is off resonance, and when it goes through, it basically shifts the energy levels around a little bit. And then we probe that with a separate beam that picks up a phase shift as a result of that change. Okay, this is called a current nonlinearity for anyone that's interested. And so our group quite a while ago developed this interesting technique to effectively isolate the effect of one photon without having to have an actual single photon source. And so basically the idea here is that if you send in a pulse of light that has some number of photons in it, and you measure the effect of that pulse, so you get some kind of phase shift in time, and then you also detect whether or not a photon was detected after the medium, it turns out that in the limit that this detection probability is small if you bin your data into basically trials where some photon was detected and trials where a photon was not detected, and you take the difference between those two, it turns out that that gives you the effect that you would have gotten if you had sent in a single photon. Okay, so it's kind of a nice trick to isolate the effect of like having a Fock state without actually having to have a Fock state. Okay. And so one thing about this is that basically you can think of it as sort of like a Bayesian technique. If you imagine the photon number in the pulse as sort of a Poissonian random variable, when your detector fires, you get some information about what that photon number was, and your sort of post-selected average, it turns out, is one photon higher than it would have been if the detector didn't click. Okay, and so this post-selection is telling you something about the photon number in the pulse, but it also only works for photons that are transmitted through the medium. Okay, but in these experiments, basically, since the signal is pretty far off resonance, all of the photons are transmitted. So this extra piece of information that you get that the photon was transmitted doesn't really tell you much because everything is transmitted. So it basically just tells you that you had kind of one extra, let's say, typical photon in your signal. Okay, so just keep this in mind. So a few years later, a PhD student named Josiah Sinclair was working on a slightly different kind of nonlinearity and was wondering basically if you could use the same technique to isolate the effect of one photon. So in this other nonlinearity, we have a simpler level scheme. So we just have two levels. And this here, we've got the signal resonant with this transition and a probe beam that's sitting off resonance. Okay, so now this nonlinearity happens because the signal comes in and sort of weakly saturates this transition or excites some atoms. And this changes the index of refraction, which is then measured as a phase shift on the probe. Okay, but since this signal is resonant, most of that light will be scattered off in other directions and will not end up transmitted through the cloud. Right, and so we started wondering, well, what if you tried to do the same trick of post-selecting on a photon after the cloud to isolate the effect of one photon? Because in this case, you know that you had the effect of one photon, but it's specifically one photon that was transmitted through the medium. And here we have a situation where most photons are not transmitted. Okay, so we had this question, like, basically, will we still get a phase shift if the phase shift is caused by excitation, which is normally followed by scattering and loss, but we post-select on not getting any scattering and loss? Okay, so in other words, our original kind of question was, do transmitted photons still excite atoms along the way, even if they're not scattered anywhere? Okay, so yeah, a couple possible intuitions that people had when we first thought of this question. So one thing you might imagine is that this resonant photon is going in, and you can imagine exciting an atom. And if it does that, it's very likely to be scattered off in some other direction. And so perhaps if it wasn't scattered, it maybe didn't excite any atoms, and we just won't measure a phase shift. Okay, that's kind of one intuition that you could have. But then you can also say, well, no, that picture seems too naive, because in reality, we know that light is just an electromagnetic wave. And everywhere that it's present in this medium, it's kind of polarizing the atoms. It's rotating them slightly up the Bloch sphere, giving them some probability to be excited. And if a photon is transmitted, that would seem to indicate that it saw the entire medium. So it had a chance to kind of polarize all of the atoms, whereas if a photon scatters, it only sees part of the medium and then it scatters somewhere. So maybe by that logic, we should expect transmitted photons to be giving us larger phase shifts. And I've kind of labeled these two intuitions, either scattered photons are doing most of the work, or transmitted photons are doing most of the work. And keep these in mind because they're going to show up later in the talk. Okay. Right, so shortly after coming up with this question, we sort of realized that this question can kind of be reframed in terms of time. So we're measuring a phase shift due to this excitation, and this phase shift that we get on the probe beam is proportional to the probability of having atoms excited in the medium. And so we thought, okay, well, in some sense, if you basically measure that probability and integrate it in time, this will give you some sort of measure of the total amount of excitation that occurred as the photon was passing through, and it has units of time. So it seems like a pretty reasonable definition of the time that the sort of energy of this photon spent in the form of an excited atom, essentially. So we call this the atomic excitation time. And this turns out to be very closely analogous to something called the dwell time in quantum tunneling, which is actually another thing that's measured in our lab. Right, and so now we have this new kind of question of how much time does a photon spend as an atomic excitation while it's passing through a cloud of atoms? And in particular, does it depend on what happens to that photon? Okay. All right, and so with this definition, it turns out that you can actually very easily calculate what to expect on average, meaning if you don't post-select on the photon scattering or transmitting. And you can see that by seeing that the rate of scattering from the medium is just given by this kind of the line width of the atoms, gamma, times the probability of an atom being excited. And so if I integrate both sides of that equation, on the right side, I just have gamma times this definition of our excitation time. And on the left side, I have a time integral of a rate of something happening. So this effectively gives me like a number of scattered photons. But if I only start with one, if I imagine just sending a single photon into the pulse, into the cloud, sorry, this will effectively give me the probability that that photon is going to scatter. Okay, so I can rearrange some things a little bit. And we get that this excitation time, on average, is given by the probability that the photon scatters times 1 over gamma, which is the lifetime of the atom. Okay, so this would seem to kind of support the first intuition that maybe scattered photons are doing all the work, in the sense that the easiest way to get this average would be if when a photon scatters, it spends one lifetime as an excited atom, and if it transmits, it spends no time at all. Right, that would give you this kind of nice, clean average. And so partly based on this, we expected that if we measured this effect of transmitted photons, we should see 0 effectively. Okay, so that kind of cliffhanger, moving on to part 2. So any questions so far? No. Okay. All right, so I mentioned in this section that we have basically, we first did an experiment to measure this because initially we didn't know quite how to solve this problem theoretically because it's quite challenging as a result of all the loss that you have in the problem. And so we went ahead and just measured it. Okay, so let's talk about how one would actually measure this thing. So it's a similar setup to before. So we still have a cloud of cold atoms. We have our pulsed signal beam, the CW probe. And so we send in this resonant signal photon, and it kind of saturates the medium slightly, passes through, we get some kind of phase shift. Again, this phase shift is proportional to the probability of having excited atoms. So if we integrate this signal in time, we'll get something proportional to this average excitation time. And then you can also then post-select on detecting a photon in this transmitted mode. And you'll get some sort of a priori unknown signal. If we integrate that signal, whatever it is, that should give us something proportional to this excitation time caused by a transmitted photon. Okay. All right, so this previous student, Josiah Sinclair, did this experiment. And essentially what he found, so this is the trace of this phase shift in time. You can see that it's not 0, there was a bump. So we kind of disproved the hypothesis that perhaps transmitted photons should spend 0 time and scattered photons will spend a lifetime. But in this experiment, effectively, we were only able to work in one particular parameter regime. So we got one data point after a month of taking data. So this is for one particular optical depth of the cloud, so a fairly optically thick cloud, and for a fairly broadband pulse, so like shorter than the line width of the atom, or the lifetime of the atom, sorry. And so we got some kind of result that was non-zero And it was sort of consistent with a few different semi-classical models that we had at the time. But these models were not particularly convincing. So we teamed up with a theorist named Howard Wiseman to figure out how to actually kind of calculate this thing properly. Okay, so that's what we'll talk about now. So quantum mechanically, we describe this system. So we have our single photon pulse, okay, heading towards this atomic medium, which we model as some continuous medium with some kind of coupling constant G that determines basically, how quickly you couple from light to atomic excitation. And the state of this system is in general going to be some entangled superposition of some probability amplitude to be a photon at position X with no excited atom, and some amplitude to be what we call a collective atomic excitation at position X with no photon. Okay, so this would be, you basically have a single atomic excitation that's spread over some number of atoms. So there's one total excitation, but you don't know which atom is excited. So it's kind of a coherent superposition of them all. Okay, so this is sort of a wave function for this single excitation, which at any time can either be a photon or an atomic excitation. Okay, and then we have this Hamiltonian, which governs how things evolve. So basically, this is just kind of a standard Hamiltonian for the atoms and the light, plus this dipole coupling term, which will again couple, the photon mode to the atoms, together with this non-Hermitian loss term to model spontaneous emission effectively. And so we kind of start out with basically alpha being kind of a Gaussian pulse headed towards the medium. And then as it propagates, the norm of this wave function is going to decay because we're using this non-Hermitian Hamiltonian. And we'll get some conversion between light and atoms. And then in order to define and measure this excitation time, we need to come up with some sort of operator to do this, right? And so we define this excitation probability operator of basically projecting onto the atomic part of this Hilbert space and integrating over all position. Okay, so the expectation value of this thing tells you essentially the probability of that single excitation being in the form of a coherent atomic excitation as opposed to a photon at any given time. And like we said, if you kind of do this integral, you get this nice average answer. Okay, and then the tricky part is if we want to determine what will happen if we weakly measure this probability operator and post-select on the photon being transmitted, we need to use something called the weak value formalism. And so essentially what this says is if you're doing a measurement where the noise is much larger than the signal, and you start out in some state psi, and you post-select on finding your system in some other state psi t, then your conditional average is going to be given by this quantity. And I should mention that because this is not an expectation value, this quantity is not constrained to lie, for example, within the eigenvalue spectrum of this operator. So you can get a negative number, you can get a complex number. So in general, we have to take the real part of this. But so the real part of this is going to correspond then to our time that a transmitted photon spends as an atomic excitation. Okay, and so we have this formula, and we can generate equations of motion for these alpha and beta coefficients and solve for this time. And when we did this, we found something quite strange. So essentially, this is the time that a transmitted photon spends as an atomic excitation as a function of the optical depth of the medium and for different pulse durations. And what we found was that for a bunch of parameter combinations, this time is actually negative. Okay, so we were quite confused by this initially and assumed there must have been a problem in the code or something. And there were some problems in the code, but we fixed them and it was still negative. And so yeah, so we got this result and we were quite confused. And I'll mention that the first experiment that we did on this plot corresponds to something like maybe this yellow point here. So we did expect to see a positive number, and we saw a positive number that was somewhat close to the theory. And for technical reasons, we couldn't get into this other parameter regime. But it seemed like, okay, if we could have, we would have seen this kind of crazy negative answer. Okay, so we were very confused about this negative number for quite a while. And eventually we decided, okay, there's another negative time that shows up in optics. Maybe they're somehow related to each other. And so this other negative time is just the group delay. So, in optics, you have kind of two different speeds. You can have a phase velocity and a group velocity. So if you send a pulse through a medium, then the envelope of that pulse will travel at some group velocity. And as a result, it'll acquire a time delay relative to free space propagation. So that's called the group delay. So a positive group delay would mean that the pulse shows up later than it would have if it were traveling through free space. And so the really weird thing about this group delay is that when you're close to resonance, it's basically given by the frequency derivative of the phase that light would pick up as it propagates through the medium. And if you go through a resonance, the phase looks like this. And so if you take the derivative of this, you get something that goes negative near resonance. Okay, so this is sort of a well-known phenomena that was worked on in the 60s and 70s, basically. And it's this weird kind of situation where basically if you have a narrow band pulse, so all of your frequencies are kind of contained within this short region, then what happens when you send that through atoms, this is actually experimental data. So if you don't have any atoms, you of course just measure some kind of Gaussian pulse at your detector. If you put atoms in the way, of course that pulse is significantly attenuated because it went through an attenuating medium. But you can see it's also kind of reshaped in a funny way, such that effectively the earlier parts of the pulse are more likely to be transmitted than the later parts of the pulse. And this is because the atoms essentially have some delay time when they respond to the light. And so basically the back half of the pulse is more likely to scatter, meaning it gets kind of preferentially attenuated compared to the front. And so if you just look at the center of mass of this thing, it actually shifts backwards in time. So the sort of peak of this pulse arrives at your detector earlier than the free space pulse would have. So it seems like maybe there's something superluminal going on, but there's not, essentially because of this attenuation. Okay, so basically we said, okay, let's take the script delay, calculate what that should be for the kinds of pulses that we use, and we'll see if there might be some kind of relation between this and our excitation time. And when we did that, we basically found this. So here the points here are simulated excitation times for transmitting photons, and the lines are the group delay experienced by those pulses. Okay, so it was very clear that these are pretty obviously related to each other. And sure enough, we proved very shortly after that mathematically, actually, they're exactly the same thing. Okay, so the time that a transmitted photon spends as an atomic excitation, based on this kind of weakly probing the atoms technique, is exactly equal to the group delay of the pulse, even when it's negative, effectively. I should mention that this equivalence would make sense to a lot of people off resonance, because when you're off resonance, the pulse is actually delayed by some amount of time. And when we ask this question of how long did the photon spend as an atom, many people will say, well, can't you just see how long the pulse was delayed by and assume that delay time was a result of the pulse spending time inside of the atoms? And that picture, most people would say, seems to break down near resonance because the script delay goes negative. And we found that there's a certain sense in which it kind of doesn't break down. It's still true. It's just a little bit funnier because now your measurement is going to give this kind of negative time. Okay. All right, so then after after we developed that theory and saw this prediction, we, of course, spent a lot of time basically doing experimental upgrades so that we could actually get into this parameter regime to measure this thing. And this is the result. So this was a very beautiful experiment led by Daniela Angulo, who recently graduated. And effectively, so what you're seeing here is each of these traces shows a few different phase shifts. I think they're kind of hard to resolve on here, but basically, so if you can make out the colors, the green points here, which effectively just always look like a Gaussian. So this is the average phase shift that we get if we just send in a bunch of pulses and average all the data together. And that, matches the shape of what we expect on average. And then if you post-select, the theory says that your phase shift should look like this orange curve. So it starts to look very funny. Depending on the regime you're in, it's negative. There's sort of a dip that comes a little bit earlier than you might expect. And when we did the experiment, indeed, we found at least quite good qualitative agreement with these shapes. Okay, so here on the other side of the screen here, I'm plotting these times. So the way that we extract a time from this data is you basically take your phase shift, which again is proportional to this probability of atoms being excited. You integrate it over some time. And then because essentially there's sort of a proportionality constant between the phase that we measure and this probability operator, we normalize by the average phase shift, because basically those two measurements have the same proportionality constant. And so if we just divide the two, that kind of cancels out, and we're still, we're looking at basically just the probability at that point. Okay, so you integrate this phase over some region and divide that by the integral of the average phase in the same region, and you get these excitation times. So the data points here are data points. These kind of broad curves are the theory. So in general, we see pretty decent agreement. So this is a function of the duration of the pulse. So for more narrowband pulses, you expect that most of the frequency components are close to resonance, and so you get this negative group delay, and also this negative excitation time, which we see. And yeah, so we kind of measured some sort of negative time, effectively. And we put this experiment on the archive, and it got lots of media attention, probably too much, because of the negative time part in the title. So, okay. So what does this mean? This is everybody's first question, obviously, when they hear about this. What is a negative time? What does that mean? And to me, the only kind of satisfying answer is in terms of interference. So effectively, we measured a probability operator, which should always be between 0 and 1 if you take its expectation value. But with this post-selection, we got a negative number. And so that's what they call an anomalous weak value. And these always correspond to sort of quantum interference effects. So to get some intuition as to how this can work, in the theory paper that we wrote, we developed this kind of toy model, which is very analogous to the atomic system, but a little bit simpler because it's kind of discrete and nice to think about. And so basically, the model is that you have this Fabry-Perot cavity, so two mirrors, which are slightly imbalanced, and you send a photon at this cavity, and then the inside of the cavity is going to be analogous to basically an excited atom, so the atomic excitation. And then if a photon transmits to the cavity, that's going to be analogous to being scattered, basically because in order to transmit, you have to first go through the cavity, and in order to scatter, you have to first sort of excite an atom. And so if you transmit, that's going to be like not talking to the atom at all, basically just passing right through the medium and kind of not interacting with anything. Okay, and so then we're going to have some kind of quantum mechanical meter system that probes the probability of finding a photon inside of the cavity as a function of time. And so in general, that will have some kind of wave function associated with it. And because this is a weak measurement, it's going to be a pretty wide wave function. So you have a very kind of noisy meter that's like roughly half the time showing you a negative number of photons, half the time showing you a positive number of photons. And we're going to look at a post-selected average of where that meter ends up. Okay, so we measure this kind of dwell time, which is the same thing. So we're going to project onto this kind of cavity mode and integrate that over time. And so it turns out that if you do this, you can show that the weak value that you get can be very nicely explained in terms of interference between Feynman paths. So essentially, you can think about this as there are many ways for a photon to end up at this detector over here. So you can imagine, first of all, just reflecting off of the front mirror and never going into the cavity at all. So that would correspond to cavity dwell time of 0, right? You could also imagine going into the cavity and doing one round trip through the cavity and then leaking out the first mirror. So that would correspond to, like one round trip time in the cavity. You could also do this, infinitely many times and then come out and get detected. And basically, because this photon is very narrow band and long in time, all of these different paths are indistinguishable. Okay, so you can't tell if it reflected just off the front or off of this. You get interference between all of these things. Okay, and so it turns out that basically the probability amplitude for this first path to happen, where it doesn't go into the cavity, is positive. And the probability amplitude for any other path involving bounce around in the cavity for some time and then coming out is negative. Yeah.
This analogy, this is one-dimensional, but in your atomic system, scattered light, transmitted was in one way, but scattered was all around. So because initially you said that transmission was likely it wasn't involved in atomic excitation because that is the likelihood that we keep on in the same direction. But now you are having this one big picture. You are involved in the excitation because it's just there.
Right. Yeah. So it's so the cavity model. So we chose it specifically because you can think about like a single loss mode, and it's in the same dimension, in the same direction. But mathematically, I don't think that part is so important. Like you either have loss, to some other kind of loss mode, or I'm not sure if I'm answering this, but it's So mathematically, they turn out to be quite similar. I agree that it seems a little bit different, but right. And so effectively, because you have all these different paths that are indistinguishable, your meter system basically ends up in a superposition of where it would be for each of these individual paths. So this black wave function is what you would get if you just reflected off the front mirror. So it doesn't, it's centered at 0, and it doesn't shift at all. And then all of these other kind of green wave functions at the bottom are what you would get bouncing around, n times, weighted by the probability amplitudes of those things happening. So these are all negative, and they start shrinking because it gets less and less likely. And essentially, if you add this black Gaussian to all of these green ones, you get a shift in the other direction. Okay, and so this would give you the sort of post-selected average of the meter state. So it shifts backwards as a result of this interference. That makes sense. So basically, you have a situation where there are many different ways that a photon can spend a positive amount of time in an atom. Right, and I'll just clarify. So for the atoms, this would basically mean that you could imagine a photon passing straight through the atoms without talking to them. You could imagine it passing through a little bit, exciting an atom, and then getting pulled back into the field and continuing on its way. Or it could do that many times. And interference between these things, which are indistinguishable paths, you can't tell which one of them happened, leads to an overall negative measurement in the time. So there are many positive ways that a photon can spend time, but the fact that they interfere with each other gives you an effective negative time. It's basically the only kind of interpretation that you could really get here. Okay, so maybe I'll pause again for questions.
That's a nice Where would you put the vacuum mode in that?
The vacuum modes meaning the kind of the like loss modes.
Yeah, in that particular representation of the mirrors, you would also have some vacuum modes, right? That are reinforced.
Like the
vacuum field oscillation. Right?
Like the cavity mode or the sure.
So I'm just trying to picture. Is that part of the story at all, or?
I want to say no. I'd have to think about this more carefully. Yeah, I mean, effectively, we're measuring the photon number inside of the cavity. Yeah, yeah. Any other questions? All right. Okay, so we'll move on to the last part of the talk, which is about what happens to scattered photons. Okay, so right, we can also use the same kind of theory to figure out what happens to a scattered photon. And it turns out that in the limit of the optical depth going to 0, this is a very thin atomic medium, this time is actually exactly equal to something called the Wigner delay. So this is effectively the delay in a pulse of light that is scattered from some two-level system. And this is a sort of quantity that's, okay, yeah. So this is a quantity that is well known. It's been measured before. If you fire a pulse at a single atom and just measure it off to the side somewhere, you'll get a delay corresponding to this. The interesting thing about this is that if you're on resonance, this actually corresponds to 2 atomic lifetimes rather than 1, like you might expect. And again, this is something that people have measured. And it turns out that for higher optical depths, this total scattering excitation time is basically just a combination of this Wigner time, which is associated with the scattering process itself, plus an average group delay acquired by scattered photons. And so you can sort of picture, a photon propagating through a medium. It has to propagate at some distance before it eventually scatters. And if you just add that propagation delay to the scattering delay, you get this total delay of that photon. Okay, so here I'm showing the 2 excitation times, so for scattered and transmitted photons, as a function of the effective OD, so basically the negative log of the transmission probability. And on this axis, the average excitation time is given by these black squares. So scattered is the solid curve. So as I said, for low OD, this starts off at 2 atomic lifetimes, and then eventually it decays down to 1, essentially because for a really thick medium, the average scattered photon is going to scatter at an optical depth of 1 in the cloud. And that corresponds to a group delay of -1 lifetime. Okay, and so if you add 2 lifetimes from the scattering event to this -1, you end up with 1 lifetime, which is where it eventually saturates. Okay, and then for transmitted photons, if they're narrow band, this basically just looks like minus OD over gamma. So minus optical depth times the atomic lifetime. And if you weight these 2 things by the probability of each of them happening, you always get this kind of average line. Okay, according to this sort of, some rule on the top here. And then for broadband photons, so if you have something where it's a very short pulse in time, the spectrum is much wider than the atomic spectrum, you get even more interesting behavior. It starts out at 1 and kind of sharply dips down, basically because all the resonant components of the pulse get absorbed quickly. And yeah, let's say transmitted time actually goes positive in that limit. And so basically, given this sort of average shape the initial expectation was that this solid curve would just be sitting at 1, and the dashed curves would be sitting at 0. That would be the case if scattered photons just spend 1 lifetime inside of atoms. But instead, we have this kind of crazy distribution of different times where you've got more than a lifetime being kind of partially canceled out by transmitted photons spending a negative amount of time, such that you always get the right average. And then this distribution really varies depending on things like the bandwidth of the pulse. And then I'll just mention, I think this is kind of cute. So these original intuitions of either maybe the scattered photons are doing all the work, or either the transmitted photons are doing all the work, kind of apply here in 2 different regimes. So if you look at the low optical depth regime, here this transmitted time is going to 0, but from the negative side, while this scattered time is going to a finite number, right? And so the ratio there is blowing up. So basically the probability of scattering here is very small because you have a super thin medium, but whenever you do scatter, that photon has sort of a massively outsized effect. It's giving a much, much larger phase shift than the average photon. And so, we initially expected that, again, this would be here and this would just be 0, but it sort of follows the spirit of this intuition, if you will. And then if you look on the other end of things, here for very large ODs, you're sort of giving a transmitted photon a chance to catch up because it has to transmit through the entire medium, and therefore it acquires this very large group delay. Whereas this, the excitation time for scattered photons is just saturating to some kind of constant. And so there, at least in terms of magnitudes of these effects, the transmitted photons are sort of doing most of the work because indeed they see more of the medium. So both of these intuitions sort of hold in different regimes in a sense. Okay. So now for what we plan to do next. So what I just talked about was this kind of time due to transmitted photons and time due to scattered photons. But it turns out that you can go further than that if you want to. You can post-select on a photon scattering from a particular position within the cloud. And that turns out to be quite interesting. So as a function of where it scatters, effectively, if a photon scatters, so this is the blue curve here, so if a photon scatters right at the beginning of the medium, then it doesn't have any chance to propagate, and it just acquires this Wigner delay time of 2 lifetimes. But basically, as you go further into the medium, it acquires the same kind of group delay that a transmitted photon does, but also then acquires this additional scattering delay. So it's sort of propagating down and acquiring a negative group delay, and then it scatters and jumps up by 2 lifetimes. Okay, so in this regime, you can actually see a scattered photon also spending a negative amount of time effectively as an excited atom if you look for photons that scattered far enough into the medium. Okay, so my plan is to basically measure this, this curve, this blue curve. And in my mind, this sort of corresponds to a sort of transition between scattering and transmission. So you have, initially, you're basically all scattering with no propagation. And then in this other regime, you sort of almost transmitted, but not quite. And it's kind of a nice way to sort of bridge the gap between these 2 possibilities. Okay, so here's my plan for doing this. So the experiment is quite a bit more complicated for a couple of reasons. So first of all, the level scheme has to be different. So previously, we had a 2-level system, and both lasers were addressing the same transition. That's problematic because both the signal and probe beam are scattering lots of photons. And if they're nearly the same frequency, you can't tell the difference between them. And so we're having to switch to another transition to use for the signal beam so that they're far enough apart in frequency that we can just kind of separate them out that way. And then essentially the idea will be to have a long kind of thin cloud of atoms and image it with a big lens underneath our vacuum chamber, and then basically filter out any photons that were scattered by the probe, and then image these scattered photons onto this custom multi-mode fiber bundle that I got. So essentially, this is sort of a cheap single photon camera, let's say. So we're sort of imaging things on different fibers and then sending each of these fibers to a separate photon detector. So we can post-select on where in the cloud something scattered. All right, so in summary, we found that this question is sort of significantly more complicated than we initially expected. And the nice kind of picture is that this average excitation time that you get by weakly probing the atoms is always equal to the delay time of the light. So when the light is transmitted, it acquires a group delay. The group delay is equal to this transmitted excitation time. And if a photon is scattered, we've shown that the time delay of that scattered pulse is also exactly equal to what you expect if you measure this kind of scattered excitation time. So it's sort of this nice picture where, again, I mentioned earlier that off resonance, people might expect that these time delays are acquired because the photon is spending some time in the medium. And we've shown that that picture still holds on resonance even when things get funny, basically. Yeah, so we've recently measured this. We measured these negative times. And now we're going to try to do this more complicated measurement to sort of complete this whole picture. So thank you to everyone on the team. And thanks for your attention.
So I have a question to the theory that developed for the part one.
Mm-hmm.
So you had a non-Hermitian loss then. And okay, so if I remember correctly, so usually when you do loss, you use some lead operators, and you can do this and it's equivalent to the leader if you have just one excitation. I think that's, but at the same time, I think that in this experiment, right, like technically you have like many photons and then you do post-selections. Right, so it's not actually one excitation. I was wondering if it's like, do you know if it's like always equivalent, that if you do post-selection, you can also model it like you had one excitation, which is kind of what you post-select.
Mm-hmm. Yeah, so basically what we've proved is that when you do this post-selection and you take the difference between when your detector fires and when it doesn't, specifically the weak value of something that you measure is equivalent to what you'd have if you sent in a Fox state. So my initial guess would be that it's still fine. Yeah, that's an interesting point though. Yeah.
What lengths in the scale do you need to measure to see that transition from positive to negative?
Oh yeah, so so it's not too bad. Yeah, so in terms of like imaging resolution or something like that, it's pretty straightforward. We can have a fairly long cloud, like I don't know, on the order of a millimeter or something like that, and we're planning on breaking that into maybe like 8 different pieces. And so the imaging is kind of already figured out, and we have good enough resolution. The harder part actually is just that in order to kind of see this transition past the 0 point, you need to measure at pretty high optical depths, meaning there's not a lot of light that gets that far in the medium. And so there's not a lot of light that's scattering. And if you can't collect a very significant fraction of it, then that's kind of the limiting factor potentially. So it's more so a brightness issue potentially. So camera would be awesome if you guys get one, but yeah, current plan is these fibers. But
Interesting to use other pulses. You would use a Gaussian pulse.
yeah, so basically, let me go to the group delay slide. So So this is the group delay for narrowband light. And if you have a pulse, what we've shown is that what you need to do for transmitted photons, for example, you look at the frequency spectrum of the transmitted light and do a weighted average of this function over that spectrum. And so from that perspective, it's not super interesting. With the one kind of slightly interesting thing is that this weighted average of the group delay weighted by the transmitted spectrum is only equal to the time delay of the pulse if you have a symmetric input pulse. Basically, you need a real Fourier transform of the pulse. And so if you have something like a chirped pulse, for example, then this excitation time will still be equal to this like weighted average of the group delay, but the delay time can be different than that. So yeah.
Actually, in wave propagation, we have a terminology called dispersion. If you're talking about dispersion, you have to actually consider the group velocity and phase velocity, but you didn't talk about the phase velocity. Also is affecting the phase velocity. So this is looking to one specific problem, just using group velocity.
Well, so right. So what we found.
You have to do both. Very fast. Relaxation time, which you call it negative time. That's called relaxation.
Sure.
When the velocity is function of frequency, okay, phase velocity also is function of constant frequency. Change.
Yeah. So.
How do you respond to that?
Right. So what we found is that with this, definition of time that we have, and with this measurement, the result is just equal to the group velocity. So the thing that we measure only depends on the group velocity and not the phase velocity.
Using just actually the wave package.
Yes. Yes.
Not a single frequency in the wave package.
Yeah, I mean the kind of the frequencies matter because you need to be on resonance with the atoms and so on. But
and the phase velocity also.
Right, but at least for the thing that we measure, it turns out that the group delay is the important thing. But yeah.
Yeah. So in the interpretation of the public transfer, what exactly does this mean for measure? How would it?
Yeah, so it's measuring photon number inside of the cavity. You could imagine, maybe trying to do that with an atom in the cavity or something like this, and monitoring something about energy levels of the atom, or yeah, we haven't thought too much about details of how you would actually measure this, but.
Thank you very much, Kyle, for nice talk.
Thank you.